Hey guys, this is number I think 30 number 3 from section 7.3 in the Bluman ninth edition book. So here here basically we're doing another interval section. However, this time we don't have the interval where we're estimating the true mean. Rather, here we're estimating the true proportion. So you know how usually we have distribution and distribution right like that. And in the middle we have our mean, and then on either side we have like any data point, and then like just depends on how far the data point its probability decreases, and that's why the area on the sides really decreases but the area in the middle is so high. Well, it's basically the same thing when we have a proportion, except in the middle we don't have a mu, we rather have a p. A p is the true proportion. And it's going to be the same where our proportion as we go to the left and the right of the true proportion becomes really, 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 really small. That's why the area keeps going like smaller and smaller. Now, just like the z distribution curve, just like any like normal curve, it's always going to like approach the x-axis, but it'll never really touch it. And that's because there's a non-zero probability of having a data value really anywhere between like negative infinity and positive infinity. Well, according to z-scores, but for proportions it's gonna be between like 0 and 100, right? Because it's a proportion, it's basically like a percentage. So actually let's discuss what proportions are, but by first seeing what is the equation for the interval. Well, we know that the equation for the interval when we're estimating a true proportion is gonna be p hat minus z, right? Because it's not t, because first this is the population proportion. We're working with populations rather than samples. Another thing is that usually in these problems our n's are too big. They're like let's look at number 3. Here they said 56% of respondents on an online poll said that they were Perry Como fans if 982 are randomly selected. That's a really, really big n. Usually after 30, our n becomes normally distributed, and the curve kind of looks like a z-curve, and that's why we would use z alpha over 2. So when we're estimating, when we're seeing how far away we are from the true proportion, we use z-scores, not t-scores. With the middle always being 0 still. Like the middle will always still have 0 because z-scores go from negative infinity to 0, and then from 0 to positive infinity. I said 0 weird, I just realized that. Anyways, so this, and then times the square root of p hat q hat divided by our n, and then my proportion in the middle, and then p hat minus plus this time plus z alpha over 2 times the square root of pq, same it's gonna be the same equation, just here it's gonna be minus, here it's gonna be plus. Okay, so first of all, let's see what is p hat. Well, let's say I have, I don't know, a certain food, okay? And this food, I know that, let's say I cooked it for so many people, and I asked them to like fill out a survey, and 80% told me that they really like this food. So that 80%, that's gonna be my p hat. And so it's gonna be also 0.8, because again, when we're doing calculations, we really don't use percentages, because then you have to divide them by 100. But you always want to use the decimal version of them, which just like divide this by 100, it'll become 0.80. Okay, so now we need to know what is q hat. Okay, well, what is q hat? Really, it just means it's the opposite of, or it's the complement to our p hat. So proportions have to also add up to 100%, because 100% of the people who did my survey, right? So it's gonna be 100% minus the 80% who did like my food equals the 20% who said that my food is bad. Okay, so again, we don't want to work with percentages. We would rather work with decimals because that's how we're gonna use them in calculation. So it's gonna be, instead of 100, it's just gonna be 1 minus 0.880 to give me 0.20. Now, so what is that telling me? that actually gives me an equation that I can always use for Q hat. Q hat is just 1 minus P hat. Okay, well now I know what Q hat is. So we know what P hat, we know what Q hat is. Z alpha over 2 is just our Z score, just how far away on the Z curve we are, so like, or how far away from the middle basically, how many standard deviations away we are. And so now we just need to start applying all we know from the problem to figure out this equation. Okay, so it says 56% of respondents to an online poll said they were Perry Como fans. So my proportion right here is gonna be 56% or 0.56. Okay, good to know. So what is my Q hat? Well, this is just gonna be what we just learned right now. It's gonna be 1 minus my P hat. It's gonna be 1 minus 0.56 to give me 0.44. Okay, perfect. Now we have our P, we have our P, and we have our Q. Okay, so what now? What did they say? They said if 982 randomly selected people responded to this poll. So our N is 982. Okay, randomly selected people responded to this poll. What is the true proportion of local residents who are Perry Como fans? Okay, so now we are just estimating the proportion right here, and it says estimate at the 95% confidence level. So my confidence level is 95%. This is going to be helpful. Now, if you guys remember from section 7.2, we would always go to this table to find the z-score. Actually, before we go there, let's just, wait, how do I resume? Let's just resume. Okay, let's just look at the distribution. So, okay, my distribution looks like this, because this is a z-curve, right? Because again, we just said it's n larger than 30, so it's gonna look normal, so it's gonna be a z-curve where my middle is 0. Okay, so this is z-curve. Now what? So they told me that we want to be 95%, that's our confidence level. So that means that I am 95% sure that if I choose my proportion, it's gonna be the z-score of that proportion, because you know how every proportion would be related to a z-score, would be between these two values that we're gonna find out. Again, because it's symmetric, this number right here and this number right here, the magnitude of them will be the same, like the absolute value of them would be the same, but one in reality is negative and one is positive. Okay, again, each proportion will have a z-score, and then each proportion will have a z-score, and then that z-score will basically show us the proportion curve reflected on the z-curve, and so however far you are will be like, you can actually translate it back into a real proportion so that you know how far away from the true proportion you are. Okay, so we're not going to actually find out the proportion. That doesn't really concern us right now. What we're more worried about is just the z-score, because the z-score is going to be enough to calculate the interval. Okay, so I know that I am 95% sure that it's here, so 0.95, that the z-score of my proportion will be somewhere between this unknown value x1 and this unknown value x2. So I am 95% sure that if I have a proportion and I take its z-score, that z-score is going to fall between x1 and x2. Okay, well, we need to find what x1 and x2 are. If I'm 95% sure that it's in the middle, that means I am 100% sure minus my 95% sure, right? To give me 5% unsure that it's going to be in the middle. So I am 5% unsure that it's going to be in one of those, or like I'm 95% sure it's not going to be in those pink regions, but there is a 5% chance that they might be in the pink region. So if there's a 5% chance they might be in one of those pink regions, that means not each single one of them is 5%, because then I'm 10% sure that they're in the pink region. Instead, I am only 2.5%, which is 5 divided by 2, 2.5% sure that it's gonna be in one of those pink regions. Which if I just translate it into a decimal or into a decimal, it'll just be 0.025. You basically just divide by 100. So the area under my curve right here is 0.025. The area underneath here is 0.025. Okay, so now that I know my area, I can backtrace it to find my z-score. So there's two ways to do this. The calculator and just a regular table. Let's go to the table first. Let's go to the table. I think you can use a lot of tables for this one, but let's look at it first. Wait, did I... Okay, yeah. So first, let's start with this table. I know it's called the t distribution, but there's a nice, cool trick about this problem. About this table. So, okay, well, don't worry about the degrees of freedom, right? Because this is really, really big. We're not gonna be concerned with the degrees of freedom. However, I want you guys to look at the 95% confidence. Okay, so let's look at the bottom. The bottom, see how it says Z? Infinity. Well, I mean, we don't have infinity really, but we are pretty close to, not infinity, but we are pretty close to a normal distribution because we have such a high sample size. So what I'm gonna do is I'm just gonna assume that I have, well, I'm not gonna even assume, I know that I have a Z. So I'm just gonna go all the way to the 95% right here, which is going to give me 1.960. Okay, so I know my Z, alpha over 2, is going to be 1.960. Okay, well, let's check that. How are we going to check it? Well, we're going to look inside and then go out to the fringes using just a regular z-score table. Okay, well here they're too high, see 0.999. We're all looking for 0.0, right? So it's gonna be somewhere in here. This is 0. Too many zeros, so it's gonna be somewhere. Look at that. This, oh my god, I'm so sorry. Let's see if I can erase it. Okay, well, let's say I went here. Well, this is 0.0287. That's a little too high. 81, still high, but a little lower. We're getting close. We're getting somewhere. And closer, even closer. Exact. This is exactly what I'm looking for. Okay, so let's trace this back. Well, I know that I have negative 1.9. 6. Okay, perfect. So it's again confirmed. Even though it is negative, just like the t alpha over 2, we only really care about the positive. Okay, so here I know that this is negative 1.960. This has to be positive 1.960. And even though one is negative, one is positive, we only care about the value. We don't really care about the sign. One thing again also is I know that because the curve is symmetric, right? So then if this is a value right here, this is going to be the same value, just a different sign. Because one is to the left of 0, so it's going to be negative, and one is to the right of 0, so it's going to have to be positive. Okay, well, now we know that. Now third method. So first method, use t-distribution. Use t-distribution curve. But go to the last row. Second method, use z, are they called the z-tables? Oh, standard normal distribution, sorry. Well, I mean, it's the same thing. It's like a z-curve. So now it's gonna be, use standard normal distribution, standard normal distribution table. So So this is actually table F in the book. It's in the back of the book, and this is table E, if any of you are wondering, because this is the Bluman 9th edition. I don't know if the 10th edition is the same or if, but I'm pretty sure all of the books have it. Just look around for it. And then the last problem is when the last way I'm gonna do this is I'm gonna use my calculator actually, which is really helpful in situations like this. So clear this. Let's use my calculator, and then it's 1.960 is my z. So let's try to confirm that. Well, how can I confirm it? I'm gonna look here. Again, I think you guys by now should know how to use and how areas work, especially with like normal distribution curves. Like the calculators only give you the area to the left. Even the tables give you the area to the left, right? That's why we're looking for 0.25. So again, I'm just gonna state it really quickly. If I want this number right here, which I know is now 1.960, but if I want this area right here, the calculator only understands the area to the left, and so does the table. So does the z distribution table, the standard normal distribution table. They only understand this area to the left. Okay, well, if they only understand this area to the left, then that means I can't use the area to the right, right? So I'm gonna have to calculate this bigger area, right? Well, we said here it's 0.95 because I am 95% sure that the z-score of my proportion will be between negative 1.960 and positive 1.960, like standard deviations away from my true proportion. So again, we're not looking at the proportions themselves, we're looking at their correspondent z-score. Okay? So if I have a proportion, its correspondent z-score is going to be between negative 1.96, positive 1.96. Not that it really matters right now, but this is what it is. So anyways, if I want to use this z-score, if I want to find it in the calculator, then I'm going to have to use this big area right here and this small area. So I know that this is 0.025 because we just talked about it, and this is 0.025. So this is going to be the 0.95, this big area right here. So 0.95 plus this small area right here, 0.025, to give me 0.975. Okay, so now what I'm gonna do is I can either use that, or another way to do this is I forget about this, right? And because it's symmetric, I know that the pink region, this z-score right here and this z-score right here will be the same, just different sign. So instead, I can just use the area to the left of this, so from this to negative infinity, right? So now that's exactly what I'm gonna have to use. I'm gonna do second and then vars, and then I'm gonna go to the inverse norm, number 3. Because again, we're doing z-scores. So it's gonna be 0.0... Oh, wait. Where did I do this? Second vars, inverse norm. It's gonna be 0.025, comma. My mu is always 0. When I'm doing standard normal distribution, I think it's called. Yeah, standard normal distribution, or my z-table, or my curve. My mu is always 0, and my population standard deviation is always 1. And so look at that. I ended up with negative 1.9599963. Like, this is really, really, really close to just 6, right? Like, we're not that far away. So let's just assume it is negative 1.96, and this is positive 1.96. So now you guys saw all 3 methods: calculator, t-distribution curve, and standard normal distribution table. Wait, I mean t-distribution table, standard normal distribution table. Okay, so now that we have all 3, okay, so now that we do all this, we need to just plug it back into this handy dandy equation. Oh my god. Sorry, I realized that my book is not open. Okay, I'm gonna have to go back. Isn't stats fun? Where is it? Okay. Yeah. So now, let's look at the problem. We are gonna do it. We're just gonna plug it in now. So I know my n, I know my p and q, I know my z alpha over 2. We have everything. Let's just start plugging stuff in. My p hat, well, we set p hat as 0.56 minus z alpha over 2, 1.960, times the square root. P is 0.56 times 0.44, that's p and q, divided by 982. And then my proportion, then same, zero 0.56 times 0.44 over 982. Well, okay, so now I just use my calculator to just get all these numbers. 0.56 minus 1.960 0.56 times 0.44 divided by 982. Am I doing this right? Okay, there we go. So let's enter this guy. And so this is going to be 528.95. And then my p. And then it's going to be the same, but now plus for the other side. And so that's going to be... Wait, did something happen? 0 times 50.56. Okay, so no, that's fine. Yeah, and then times 591 point, wait, 04. Oh, okay. Yeah, I was like, something is wrong with these numbers. Yeah, so actually it's times e to the power of 10 to the power times 10 to the power of -3, so that really means I have 0.528, which makes a lot more sense. And well, not even 8 because there's a 9 after it, so this means I have here is 9, and then my second one is gonna be 0.591. Yeah, that's it. So I was like, this proportion should be less than 1. What is happening? Okay, well, so now I know that my proportion, or my true proportion, actually lies between 0.5 to 9. That's worst case scenario. Best case scenario is 591, which is like almost 60.60. Okay, so yeah, this is it. We just estimated the true proportion of the people who like, I think his name was Barry Como or something like that. Yeah, so oh lord, what just happened? Okay, sorry guys. Okay, bye.